students and their parents, I'm going to give a somewhat different kind of talk. I want to talk a little about my background in history and, from my days as a student, how did I get into computer architecture? And so the title of the talk is actually From Galaxians to RISC-V. So this is, how did I start out in this computer architecture business? So when I was a kid, one day in 1979, a long time ago, that time I grew up in England, and we'd have fairs that would come around. They'd travel from town to town. So in the summer of 1979, this fair came to my town. And that was the first time I ever saw a video game. And it was a full color. It was actually the first full color arcade video game. And I was just blown away. I'd never seen anything like this before. There's this game called Galaxians. So this is a screenshot of this game. So this is an old video game. I was just a young kid then, and I was like, wow, this is incredible. Just to put this in context, this was right after Star Wars. The first movie came out in 1977, I think. So a couple of years later, I think the game authors were inspired a little bit by Star Wars. So I was a young kid. I was very excited. This was amazing. I'd never seen a video game before. Just imagine you've never seen a video game and you're a kid, and all of a sudden you see a video game. This is great. This is what I want to do. I want to spend all my time playing these games. So after that, they kind of spread around. This first game showed up in this traveling fair, but then quickly in the town, these arcades started showing up, and there was a video game arcade. So I was a kid, and it was only a 3-minute walk from my house. So of course, I spent all my time in this arcade, and I spent many hours. And I was in England, so it was 10 pence, 10p to play a game. So I spent a lot of cash at this arcade playing games, and I would get stuck there. My mother would have to send my sister over to come get me to come back for dinner, because I would just stay at the arcade all night, hang out with my friends playing games. But I was excited by the games. There's lots of different games, but after a while, I was like, I'd like to design my own games. I like playing this game, but I don't like this part of the game. This seems a bit funky. I want to do something different. I want to change it. So how do I design my own video game? So I used to know the owners of the arcade. I was there so much, I got to know the owners and the people who worked there. And so I'd start opening up the video game arcades and looking in the back, what's in the back of this big machine. And I'd see all these circuit boards. And I was like, well, I don't really understand this. I don't know what all this is, but I need to know how to do this. So I became really interested in how do I design my own video games. Unfortunately, my parents were, they were up for buying me a computer. And this was not that common back then. This was in the early, late 79, 1980. And they actually agreed to buy me a computer. And at that time, for example, my whole school had one computer for everybody in the school. And then I wanted my own computer, and this was a bit unusual. But my parents, let me buy this thing. It was called an Acorn Atom. So it was actually from Acorn, the computer company in England. Here's a picture of the machine. And this was, for me, it was great because it had 12 kilobytes of memory, so not megabytes or gigabytes, but 12 kilobytes of memory. And a special thing for me was why I wanted this machine was because it had high resolution graphics, so I could do games. But at that time, high resolution graphics meant 256 by 192 pixels total, and it was only monochrome, right? And I only had a black and white TV to plug it into. But this was, for me, was an amazing platform to try things out. It was a very small machine, but I was excited. I could write games, I could do graphics, I could do sound on this little machine. So it was a 1 megahertz 6502 processor. It came with BASIC in the ROM, but also, importantly, it had an assembler. So not only was I writing in a high-level language in BASIC, but I got to learn the assembly code of the machine and how to program the 6502. And if you want to make video games go fast, especially in that era, you had to learn the machine code, like the native language of the machine. How does it actually work? So I spent a lot of time programming in assembler. And the other thing was when I finished the program, I had to save it. But the only way of saving it was to cassette tape. Now, I think some of the students here have probably never seen a cassette tape player or a cassette tape. So here's a photo of a cassette tape. I mean, this used to be what we played music on, stored music on, but it was also the medium for storing things on the computer. But it was incredibly slow. It was only 300 baud, which means 300 bits per second. So you're used to your internet connection, which these days may be 100 megabits per second or gigabit per second. But this was 300 bits per second. So it was a bit faster than typing when you were saving and restoring to tape. And I remember I actually got the computer before I had a tape deck. So I used to have to type in the program I was working on after I powered it up. Then I'd work on the program. Then I would write it down in a notepad, and then I would turn the machine off. The next time I'd have to power the machine on, I'd have to type it all in again until I got the tape deck, which was a big advance. But this was a lot of fun. So this was in my teenage years. I was just spending all the time, playing games, learning how to write games on this machine, as well as playing games at the arcade. Now, the thing was, how did I learn to program? So the schools didn't really have didn't really have a curriculum around computers. They were just new. They only had one computer in the whole school. So the way I learned to program was actually, I bought magazines that were computer game listings. So there were these magazines you could get that had programs written out that you could type into your computer and run to play games. But I didn't have any teachers. There wasn't any programming materials. So what I did was I just figured it out by reading the listings in the computer magazines. And I remember, how confused I was when I started out. I didn't really know how things worked. I was just trying to understand. And I remember one thing was one of my big breakthroughs was I used to read these listings, and in BASIC, there is this rem statement, which is actually a remark, which is a comment that the programmer put in the code. But it took me a long time to figure out that when it said move spaceship 1 step left, that was not the computer doing anything with that. That was just a comment for the programmer. I was trying to figure out, how did the computer know how to move the spaceship 1 step left when I wrote this in the code? And it took me a long time to figure out, oh, this was just a comment. And the other stuff was actually the code that did anything. But this was how I learned, was just looking at these listings and just reading the stuff that was in the magazines and entering them in my computer, seeing what happened, modifying, just playing with it and seeing what happened as I learned to program. After a while, I got more experienced. I got more idea what was happening. I understood the assembly code, the machine code, and started writing a lot of video games in assembler. Now, one thing, the parents should realize, once you get into creating something, it's a lot more fun than consuming. Just sitting there and playing games. After a while, once I got into writing these games, this was much more fun than playing the games. And I basically stopped playing video games. I used to write them and have my friends come and play them. And I would just be interested in fixing the game and adding more features or doing something to it. I didn't really play the games that much after that. I remember one of the highlights was one evening I set out deliberately to write a whole game. And this was a breakout style game with a bouncing ball and bricks. And I did all the graphics, the sound, and the whole program. The whole thing fit into 512 bytes. There was one piece of the memory that was only 512 bytes big. So I've managed to figure out, careful programming, how to put the whole program into 512 bytes. So these days, you'll probably find some comments are longer than 512 bytes. But the whole game, including graphics and sound, in those days, you could fit it in. And so this was very useful to learn how to make things efficient, and very limited machine meant you could, you would reason about this and you would try and make things work with very limited resources, right? And it's still a useful skill. But that was just a fun project for me, try and do a whole game in ½ a kilobyte. So now one other thing that was also very important about this machine, when Acorn shipped this computer, you didn't just get the box and the manual, you also got the schematics. So they actually gave you the circuit schematics for the whole computer. So at first I had no clue what all this meant. But over time, as I learned more, I could actually go look at the circuit board, look at the schematics, read the code, and I started to get a very good understanding of how the computer works. This was really important for me to understand it. And I think this is a great example of open source hardware. So they gave you the machine, you bought the machine from them, but they gave you everything you needed to modify it, to add hardware to it, to understand what was going on, what was in the machine. So you could take the best use out of that machine. So I think this was really important. And for me, it was very valuable, being able to see all the inner workings of the computer and exactly how everything was built. Now, a bit later, just to connect with the BBC here, so that Acorn Atom was actually an early machine from Acorn, and they used that experience to build a prototype that they bid for the BBC. So the BBC was doing an educational TV series called The Computer Program, and Acorn won the competition to supply the BBC with computers. And this was a very big, important deal for Acorn. The BBC Micro was a very well-designed machine. It was very popular, and it was widely used in the UK schools for education. They actually sold over 1.5 million of these, which was a lot for the machines at that time. And one aspect here, because the BBC had a computer program, on teaching people how to program. And notice the computer program is written with the English style program for a TV program, not a computer program. But this computer program, the TV program, was very popular. Parents bought these machines so their kids would get a head start in computing. And so a lot of these were bought for people in the home. I didn't have one. I had my earlier machine. I always wished I had this one because it had so many more features. But these are a very popular machine, very important for Acorn, and also a big success for the BBC. This was a big success in terms of education. Now, one little thread here is what's interesting is Acorn actually used these machines they built to design their follow-on microprocessor. So people at Acorn wanted to build an advanced RISC processor, and they actually prototyped, simulated the designs on BBC micros. And this is what later became the ARM processor that's now standard in the industry. Every mobile phone is based on ARM. ARM is used widely in lots of other applications. And ARM, actually, the acronym originally stood for Acorn RISC Machine. And it was Acorn in England that developed this. And they actually used these BBC micros to do the simulations of the very first ARM chips that were being developed. Now, after learning about computers, this is in my sort of teenage years. The UK, we call it sixth form. In the US, you would call it high school. And after that, I went to college, undergrad. And one interesting thing to realize at the time was that computer science was not considered a serious subject at the time. So I actually went to Cambridge and I did electrical engineering, electrical information sciences. And part of my reason was that, well, computer science was not considered that serious. And also I felt the computing part was easy because I'd done so much programming. And I really wanted to learn more about hardware electronics. That's why I took electrical engineering as my undergrad. So I learned a lot. We did a lot of things there. But one other important part was that while I was at university, I was sponsored by a company called GEC, which is the British company GEC Marconi, not the GE in the US. But the model in the UK at the time was to get an industrial scholarship. So GEC would pay me additional money, but I had to work 1 year before I went to university with GEC, then every summer as an intern at GEC, and then I had to work for them afterwards, after I finished my undergrad degree. So during my degree, I did a lot of electrical engineering, I did more computing, but then it was only really when I came back to GEC after my degree that I really got into computer architecture. And so what I think is funny is when I started at GEC, my very first day at this company, when I was only 18 and I was just finished sixth form, and this was before I went to university, what they had me do was, in the old days in England, when you bought anything that plugged into the main socket, it didn't actually come with a plug. So you had to separately buy plugs and then attach them to the cable, the mains cable, to connect to the main supply. So the day I showed up at GEC, they just bought some new computers. And I had to spend the whole day just wiring plugs on this new computer and all the different peripherals. After that, though, I spent a long time doing various projects. And by the end, in the last project, I was actually designing a very big, massively parallel computer system by the time I'd finished my sandwich course at the university and at GEC. So just to talk a little about that, and that's really what got me interested in computer architecture was, during my college years, I did electrical engineering, I did a bunch of computing, but when I left and came back to GEC, they had me work on a big project that was a European research project, developing a big computer for 5th generation AI. So this is Lisp Prolog-based AI processing. And this was really the first chip that I worked on, helped design the architecture of this content addressable parallel processor. There was 148 little processors on a chip, and we packaged many of these into a system controlled by transmitters. So there was a total of 170,000 of these little processors inside this system. And during this time is when I started reading all these papers from Berkeley about, this RISC project from Berkeley and also from Stanford. So I read about Dave Patterson and John Hennessy at that time while I was undertaking this project in the UK on the 5th generation computers. So that's what got me excited about going to grad school. Doing this project in the UK, I got interested in computer architecture. Then reading these papers from the folks at Berkeley and Stanford is like, well, that's where the action is. That's really where I want to be, is go to California, go to Silicon Valley, go to the schools there to do a PhD. And so I applied. over there. And luckily, I got into Berkeley. That was one of my top choices. And I did grad school at Berkeley. So I worked on a bunch of things, but my main thesis chip was this thing called T0. And this was the world's first single chip vector microprocessor. What's interesting back then, the reason we built this chip was to be a high performance specialized processor for running neural net training algorithms. So this was the last time that neural nets were very popular. Again, this was AI related, but I wanted to build a chip that was very good at running neural nets, and it was actually used in production by a bunch of research groups to train neural nets for speech recognition. But anyway, this was a chip I understood a bit more about how to make silicon, how to do chip design, got more interested in computer architecture. One of the other experiences along the way was when we built this chip, we needed a standard scalar processor so we could run standard software. And so we picked MIPS as the standard instruction set that we used. So MIPS was one of the early RISC instruction sets that came out of the work at Stanford. From John Hennessy's group at Stanford, they commercialized that as the MIPS architecture. And the reason I like MIPS was it was a very simple, clean design. It was the most classic of the earlier RISC designs. So we liked MIPS. We wanted to base my thesis chip on this MIPS architecture. So then we went to actually talk to MIPS to see if we could license MIPS to use in our project, academic project. And they said, sure, but it'll cost you $2 million. And that was for an academic project. And those were $92. That was a lot of money. And the thing to realize for those that out there in the industry, there was no softcore industry at that time. And synthesizable Verilog was not really usable yet. So that really hadn't happened. And so what they were really asking all this money for was permission to use the MIPS ISA design. And I thought this was crazy. Like, why would we pay this much money just for the instruction set and coding? It doesn't make any sense. So we said, no, thanks. And then I just built my own MIPS compatible core and just left out the instructions on which they had some patents. So we could use this in the project. So that's some of the history that led to RISC-V. Then after Berkeley, I actually went to MIT. So I was faculty there for 9 years. And now I'm sort of moving through my career. Now I'm worrying about how do I train the next generation of students to understand computer architecture. My model is always the best way to learn stuff is to build stuff. So I had my students there learn how to build more microprocessors. One example project we did there was called Scale. It was vectors plus threading mixed together. So this was a very, the students were amazing. Who worked on this. They very quickly put this together. But one thing here, this was also based on MIPS again. We used a subset of MIPS again in this project at MIT, because it was a relatively easy thing to do. So we kept working with MIPS. Then I spent 9 years at MIT. I really liked MIT, but I did not like living in Boston. The weather there is just awful. I missed the Bay Area, the greenery, the scenery, the weather. Also flying to Silicon Valley. This really is the center of, semiconductor universe. So I really wanted to relocate back here. So fortunately, I managed to come back to Berkeley and then started groups there. So at Berkeley, this is really the background of RISC-V. So we've done all these projects. I've done these earlier projects based on MIPS, but there was always a problem with, we were worrying about the IP issues, and also MIPS had ceased to be a popular instruction set. It really disappeared. So when we looked at some new projects, we were thinking about which instruction set to use, x86 or ARM were the obvious choices. But both of these were really impossible. The x86 and ARM were both very complicated, too difficult for a grad student group to build. Back in 2010, when we started this, ARM did not have 64-bit address space, so we wanted 64-bit. And with both of these, a big problem was IP issues that we wanted to build designs and share them with our colleagues at other universities, but we couldn't do that because of the intellectual property concern. So we could get sued for making an open implementation available. So we decided to build our own ISA, our own instruction set. So the main designers were Andrew Waterman and Yunsub Lee, who are my grad students then, and now they're co-founders of SiFive. And then David Patterson, who's pretty well known because he actually coined the term RISC for his original project. So we worked on that with a lot of help from other people. It took us a while, but in 2014, we basically finished the design of something we really liked as our own ISA, instruction set. And so it's RISC-V, pronounced RISC-V, and this is really the 5th Berkeley ISA. So Dave Patterson always regrets changing away from using RISC as a name. So we went and renamed his later projects, SOAR and SPUR. We renamed those to RISC-V and RISC-V. So that's how we get to RISC-V for this new design. So, so RISC-V, we developed it for ourselves, but we had a lot of interest from outside. And so by, you know, one thing to understand is what is an instruction set? Why are people interested? I think, you know, I like to answer that question by asking some questions like, why does instruction set matter? Why does this machine code interface? Why is that important? Well, if you look at the industry, you know, Intel just cannot sell mobile chips. And the reason is they have the wrong instruction set. All the mobile chips are based on ARM. And so none of the software runs on x86, and nobody wants x86 in a mobile platform. On the other hand, partners of ARM who build chips around ARM are having a hard time selling servers. And that's because most of the servers are based on x86 ISA that actually came from AMD and Microsoft. And it's really hard for ARM to get any penetration in the server market. Another question is, how come IBM can still sell mainframes? And the interesting thing is the IBM 360 is actually the oldest surviving instruction set. So IBM actually defined the idea of an instruction set back in 1964 when they said, okay, we're going to have a software interface that encodes the work the computer's going to do. And we're going to keep that the same, even though we change the implementation underneath. So IBM is still has a profitable business selling these mainframes. And the thing to realize, this instruction set architecture, which is how you encode software for the machine, this is really the most important interface in computer systems, because this is where software meets hardware. And you can see it kind of divides our industry, like mobile, server, mainframes. It's really segmented by the ISAs they use in those domains, because that governs what software is available to use in those spaces. Now, one thing that's curious is most of the computing industry has open interfaces. You define a specification, it's open, anybody can implement it, and you know, people compete on how good their implementations are. Also, if it's an open interface, then you can have free and open implementations. You can have an open source implementation to that standard. But up till now, we really haven't had an open instruction set. So it's either x86, ARM, or mainframes 360. And those are all proprietary. They're owned by those companies, and you need a license to use them. So they're not a free standard at all. You cannot just go build your own ARM chip or ARM core and put it on the web for anybody to use. That's not allowed. So now the big problem here is that companies and their instruction sets come and go. So you may say, well, it doesn't matter that a company owns it. Well, actually, if you build all your software around one of these instruction sets, they may disappear for a reason that's out of your control. So there used to be a very big computer company on the East Coast called Digital Equipment Corporation, and they had a lot of very popular instruction sets, including the Alpha. It was at one time the fastest microprocessors were based on the Alpha RISC instruction set. But they're out of business now, and if you based your world on Alpha, you had to go port all your code to something else. Intel, although they're obviously doing very well around the x86, they tried to move the industry to this new instruction set called Itanium, and that failed. But a lot of companies tried to tie their fortunes to Itanium, and they went under as a result of trying to go with Intel Itanium. MIPS, we already talked about MIPS. It was a very popular instruction set at one time, but it's really gone downhill since then. Recently, they were bought by a startup, Wave. They tried to open the ISA, but then they closed it down again. And now the whole MIPS company is pretty much winding down. So you won't be able to use MIPS anymore. So that instruction set's gone effectively. Spark was another one of the early RISC instruction sets. This was mainly inspired by the Berkeley work. What's nice is that in the 90s, Sun actually did open up this instruction set so anybody could license it. But then Sun was acquired by Oracle, and Oracle closed down the instruction set and also closed down all of Spark development at this point. So Spark is dead now as well. Now ARM is very important, successful company in this space. But in 2016, people were a bit shocked when they were sold to SoftBank and taken private. And then a fraction was sold off to investment firms. And now, again, ARM is in the news because they're up for sale. So in the last few weeks, there's been a lot of speculation about some, SoftBank has put ARM up for sale. A lot of different companies are interested in buying ARM, and that will really upset the industry because people had relied on ARM for their instruction set design and for their core designs. And if it's now bought by some company that may be a competitor, how are you going to build your world? So the big point about this slide really is this is not a new phenomenon. This has happened repeatedly. That when you base your world around some company's instruction set, you're really at the whim of what happens to that company. No matter what you do, all your software development, which is the big cost, is tied to that company's instruction set, and you may lose that investment. Now, the other problem with instruction sets is there's so many of them. If you look at a modern chip, it has many, many instruction sets. The applications processor, people say this is an ARM chip, but usually on that ARM chip, there'll be many other instruction sets doing things like graphics, image, radio, audio, security, power management. It's not unusual to find there's over a dozen instruction sets on one chip. So why are there so many? Well, the thing is the instruction set, like the ARM instruction set, wasn't designed for all these other areas, and it's too big and clunky to modify to fit. And so you're motivated to go use something else. Another big reason is just because the main ISA is proprietary, you cannot use it in your IP. So companies provide a video engine or an image signal processor. They cannot use ARM inside there, for example, because it's not allowed by ARM. You have to do something else anyway. So you're forced to do your own ISA. And so that's the reason you get this fragmentation of all these different instruction sets. And finally, one other problem is because of the costs here, sometimes managers allow engineers to go build their own instruction sets. And that's a really bad idea because you have to support these with software. And that's a big, big cost that people don't usually account for. So do we really need all these different instruction sets? You know, and do they have to be proprietary? And do they have to keep disappearing? You know, the idea behind the RISC-V project was, what if we had a stable, free, and open ISA that everybody could use for everything? And that's really what we did with the instruction set we developed at Berkeley. We decided this should be open, free and open, anybody could use. And we'll try and make it a standard everybody uses everywhere. So in 2014, we all went to Hot Chips, which is a major conference. It's happening on Monday. For those of you, actually tomorrow is the tutorials day. So please, you know, attend Hot Chips if you're interested in modern chip developments. But in 2014, we made a big push out of Hot Chips to advertise RISC-V, and all these t-shirts made a big noise there. And we had a very, very positive response from industry. And so, but they said we cannot keep it as a university project. It has to become more stable. And so then we set out to create the Risk5 Foundation, which is now the Risk5 International based in Switzerland. And so this is a nonprofit entity that serves the industry, providing standards for the whole industry. And the goal is to have the whole community come together to define the open standard that everybody can use for their projects. And this will be long-lived, not tied to any company, so it shouldn't disappear. Now we have members all around the world. So in China, a big contingent in China. In Europe, the European Union is funding projects around RISC-V now. In India, India was actually the first country to say RISC-V is their national instruction set. So a lot of government projects are funded for RISC-V. Japan, we've had growing interest in Japan. Also here in North America, a lot of interest. NVIDIA, all NVIDIA GPUs now ship with RISC-V cores on them. Western Digital has said all of their chips are going to move to RISC-V that they use. And so wide adoption in North America as well. Surprisingly, the biggest RISC-V event we've had so far has been in Pakistan. So in Pakistan, we actually had over 3,000 people attend a seminar on RISC-V. So these countries are interested because it gives them independence. It's an ISA that nobody owns. It also allows them, the governments who are worried about security, they can build their own implementations. They don't have to license an implementation from a different country. So all these countries are interested because of semiconductor independence and also security. So we now have many, many members in the foundation. Several hundred companies and organizations, plus a few hundred individuals are members of the foundation. This includes, you know, most of the major names in semiconductors. So you have, you know, IBM, Samsung, Qualcomm, NVIDIA, Google, Sony, Xilinx. So many companies are involved now in RISC-V, and all of them are very actively looking at how to work with RISC-V. So many members, growth is very strong across the industry. It's not just hardware implementers, it's also software, foundries. A lot of people are interested in RISC-V. So how does RISC-V work? So what we did is we came up with a standard, and the foundation, RISC-V International, they really just manage the standard. So it's a nonprofit that manages the spec. And that's the interface between software and hardware. And so the nice thing about having an open specification is it allows you to have open source cores. And so there are many open source cores available from many places. But it's not only open source cores, you also have commercial providers. So like SiFive, for example, we provide commercial license, guaranteed, verified cores to people. There's many other suppliers all around the world. And I think today, actually, RISC-V has more commercial core providers than any other instruction set in history. So this leads to, RISC-V will be a very stable instruction set to build your world around. If one of these companies goes away, you can get it from a different company. You're not tied to any one supplier or their business fortunes. And finally, you can also build it yourself. So NVIDIA on their GPUs, their RISC-V cores are ones that NVIDIA designed by themselves for their own internal use. So on the hardware side, you have this freedom of choice. I can use an open source core, I can use a commercial core, or I can build my own core in-house, and you're free to do that. On the software side, RISC-V has been rapidly adopted by the open source community. So a lot of standard open source software like GCC and Linux, all these different open source software distributions, RISC-V is a mainstream supported architecture these days. But again, it's not only open source software. So RISC-V is also heavily supported by commercial software too now. So you have commercial software providers like Lauterbach, Sega, IER. They provide tools for people working with RISC-V. This has been driven by demand. So there's commercial companies working with RISC-V. They want the same tools to work on RISC-V as works for the other instruction sets they use. So what's different about RISC-V? It's very simple. We made it very simple, and that was a lot of work to make it simple. It's very clean, very modular. It's designed to be extendable, so it can handle all those different tasks on the SoC. It's stable because we don't have a commercial interest in pushing it forward and making you pay for the next one. We can standardize and freeze the design so you have this stability in the software stack. Another big difference is designed by the community. It's not just one company. It's all these companies coming together to design this instruction set, and also the software community helping us design the instruction set. So just to give you an idea, so this is the base instruction set for RISC-V on one slide. It's that simple. And when I think back, it's when we talked to MIPS back in 1992, basically they're asking us $2 million for this. Right, here's the encoding of this instruction, looks like this set of bits. This is really all an instruction set is. Here's a string of bits in memory, this is what they mean. At some level, that's all the instruction set is. It's just the specification that you just have to all agree on. And that's what we're doing at RISC-V. There's a little bit more to it than that, but when it comes down to it, this is really all there is to an instruction set, is an encoding. So why is RISC-V so popular? I think engineers sometimes don't see the forest for the trees. They sort of fixate on, is something 10% faster or 30% lower power? But the RISC-V really changes the business model. Previously, you wanted a core, you would go ask all the different vendors, how well does that core work? And you'd pick one. But once you pick that vendor, you would get their ISA, and then you're stuck. On the next generation of that chip, you'd have to use their ISA. Otherwise, we'll rewrite all your software. But RISC-V, you flip it around and say, I'm going to do RISC-V. And now I have multiple vendors who are going to compete for my business. And next time, one of them will win. Next time around, you can use a different vendor for the same socket because they're all compatible and follow the standard. And the momentum that's building up here, even if there's some features, RISC-V is still a new instruction set, is still evolving. All those are getting fixed very quickly over time because there's so much momentum and interest in RISC-V that's filling that out. So right now, just to kind of wrap up here, our modest goal now is basically become the industry standard instruction set for everything. We're sort of working slowly toward, well, quite rapidly towards that goal. And this is really our motive, is make sure we can have the same ISA everywhere. It simplifies everybody's life. In education, talking to students out there, what you'll see when you go to college is almost all the major universities now are adopting RISC-V, and you'll see that in your classes. The undergrad curriculum around the world is starting to focus on, standardize on RISC-V. And that means for industry out there, you will get, undergrads coming out of college will be trained in RISC-V already. That's what they'll have seen in college. You'll be hearing more about this board later. This is from SiFive. This is a board to help you, practice and learn how to build embedded systems, IoT systems. This is a board. You'll hear a lot more about that later today. And really just to wrap up here, so RISC-V is really about, completing this innovation cycle. What I learned from my own past was being able to get access to how things are built. That's how I learn. And so keeping things open so anybody can go dig in and find out how things work is really key. So if everybody can use the same open platform, you can use that in education, you can use that in real products in industry. You can take those industrial problems, like problems industry's having, take them back to a research group. They can work on something and immediately feed that back and have it be applied. So that's really the goal of RISC-V, is building this open ecosystem. Research, education, industry all work together on the same thing. Okay, thanks. I'll wrap up there. It's about time.
Oh, thanks for Professor Asanovic's great sharing. It's already a lot of questions from our audience. So the first question is from Cassie. I guess she's the mother. So the question I think is asked about Krista's parents and Krista as a parents. What's your attitude when you were spending so much time in arcades playing games? Were your parents worried? Did they try to stop you? What happened? And if you, as the parent, when your kids play a bunch of games, what would you do?
Yeah. So when I was a kid, I think I was always doing well in school. So they weren't really worried because, you know, I was doing fine in school. They did worry about, you know, they would come and get me sometimes because I spent too long at the arcade. But I was doing fine in school. So they were like, always okay. You know, he's doing okay. And, you know, doesn't seem to be a problem. Now, as a parent, I have a 6-year-old, 6.5, and he spends a lot of time on the games. Unfortunately, now with COVID, you know, we can't do as much. You know, I wish he was outside playing with the kids and doing stuff. We try very hard to keep him off the iPad, but sometimes you know, we just can't. And again, he seems to be doing fine. You know, he seems to be doing well at, you know, the things he does study. So I'm not so worried. But I do think back to my parents. I think as long as they're doing fine at school and, you know, they have friends and they seem to be doing okay, I don't think it's a big worry. I don't think people should worry.
Okay, thank you.
I'm trying not to worry about my kids.
I guess you will comfort a lot of the parents here. Thank you, Professor. And the next question is from Charlie. His question is how to start to work with open hardware by GitHub.
How to work? Well, I think there's, at RISC5 Foundation, there's actually get started with RISC-V guides. There's some how-tos on how to get going. And we need to improve those resources, but there is some resource there that tells you how to get going. And I think, you know, like with the event board and other things, we're trying to SiFive also to build more guides to get people up on, you know, dev boards and to understand how things work. My group at Berkeley as well has a project called Chipyard, which is meant to be an open environment for building SoCs. And we're trying to make that well documented so people can learn there as well. So there are a lot of resources, a lot of websites. It is hard sometimes just to navigate. Sometimes there's so much, trying to figure out the right path to get going. But the foundation and the SiFive, we're trying to make that a bit easier. Yeah.
Okay, thank you. So the next one is from the Eric Zhang. The question is, what would happen if you took a modern day computer and gave it to a computer company from back then?
Took a modern day computer, give it to a company back then. I'm pretty sure the engineers would start using it for their simulations. Like all the engineers out there know that you spend all your time waiting for simulations to run. So you would use the computers to run simulations to let you build faster computers. So,
okay.
Yeah, so back when, you know, when Acorn was designing ARM, they used the BBC Micro to design the ARM. I'm sure if they had a faster computer, they'd have got more done. But yeah, I think we would just use it to run our simulations to do more engineering.
That's fast. Thank you. And the next one is it possible to have is it possible to have a compiler to recompile the binary code for one ISA to run in other ISAs?
Yes, so that's been a standard technique. I think Apple has been the master of this, actually. They transitioned instruction sets several times. The first machines were 6502 based, then the Mac was a 68000 based machine. They then moved to PowerPC, which was, they did a binary translation to go from 68000 to PowerPC. And then they went from PowerPC to Intel x86, and they did another level of binary translation there. And now they're going to Apple Silicon, which is actually ARM-based silicon. And it'll be interesting to see how they go from x86 code for Apple to that. Now, one thing is Apple has built a development environment that makes it easy to change instruction sets. You can recompile. But a lot of code out there is native for a given instruction set. There is a lot of industry know-how and how to do this, but it's not as great as recompiling natively. But there is a lot of translation technology out there from various people. I think Apple has actually been the masters at doing this. They managed this ISA transition several times. Yeah, actually, I I talk about that Galaxians game at the beginning. I actually have that game in an emulator, but the emulator is written in PowerPC code. So I have an Intel x86 machine that runs the PowerPC emulator for the original 8-bit micro that ran the game. So there's 3 levels of emulation right there. So I can still play that game from my days as a kid. So.
Okay, thank you. And the next one is from the latest, hottest news. It's about NVIDIA. NVIDIA is set to acquire ARM. How do you think it will affect RISC-V and SiFive?
I don't know what will happen there. I think what people see, like I said in the slide, the big advantage of RISC-V is stability of supply. So you know that no matter what happens, there'll be many suppliers of RISC-V cores, and it's not owned by any one entity. So it can't be bought and sold. It's an open standard. So I think the big advantage for RISC-V is it is stable and open. And I think a lot of people are looking at what's happening and thinking, this is not as stable as we thought. And but it's the same story playing out yet again. This has happened many times in the past, like I tried to outline. This is not a new phenomenon. But I think we can hopefully move the industry to a single, stable, open standard, so they don't have to worry as much in the future. So I hope, I think people appreciate what we're trying to do with RISC-V now, and hopefully get even more traction.
Thank you, Professor Asanovic. I think these questions pretty much covered most of the questions asked by the audience. What a great value of the past half an hour. Thank you so much, Professor Asanovic, for sharing so much insights about the STEM education, chance of the semiconductors, IoT, especially the gaming experience. I bet your generosity to share has already inspired so many students and the parents and the hopefuls who are looking for the opportunity. Again, thank you so much.
Okay, thank you for having me.
Thank you.